Hello everyone. Today we'll be taking a look at a problem from a Jane Street quant trading mock interview, which I've also posted on my channel community page about a week ago. Even if you have taken a look at the problem, do stay tuned for this video because I'll be doing a more general version which leads to some interesting number theory problem. And also I noticed from the comment section that a few of the viewers may have misread the problem. So without further ado, let us take a look at the problem. So for this problem, I let n bigger or equal to 3 be an integer. And this problem involves two players, Alice and Bob, playing a game. So Alice first picks a number x among 1 to n. And then Bob knows the number that Alice picks and is required to pick a different integer y among 1 to n. Then a fair n-sided die is thrown which uniformly picks at random an integer z among 1 to n. The player whose integer is closer to z will win z dollars. So in this case, in this particular instance, the number z turns out to be closer to Alice's number, so Alice will win z dollars. Notice that the amount of money you win is actually equal to the value that the die land on. It's not a flat rate, so if the die had landed on a larger number, you would have won a bigger amount of money. Now the question is, for which integer n is it better to be Alice than Bob? So in the original Jane Street video, actually the number n is chosen to be 30, and the question is it better to be Alice or Bob? And in my community post, I've chosen the number n equals 2023. And actually, some small amount of care is needed when you pick your number n for those questions, because there are some values of n which will make your life quite significantly more difficult. And we will take a look at this as we go through the problem. So first of all, how will you think about a problem like this? Well, a good way to approach the problem is to say, okay, let's say Alice picks a number k, then what should Bob do? What is optimal for Bob? Well, clearly Bob wouldn't pick a number that has a gap away from k, because you are giving up half of the numbers to Alice's territory, so to speak. So if Bob picks a number like here, then if the die lands on any of these numbers over here, Alice will actually wins. But you could have just picked the number right next to Alice's number, and then you will cover all that number as well. So it's strictly better to always pick the number just to the right or to the left of Alice's number. So the question is, should Bob pick to the right or to the left of Alice? Well, then Bob will have to evaluate his expected earnings from the two choices, right? So that leads to a natural question of how do I calculate the expected earnings? And in this case, it is quite easy. I define the territory of the player to be basically if the die land of that number, then that player will end up winning. So you can say that, for example, in this case, if the die lands on any of 1 to k minus 1, Bob will end up winning. Whereas from k to n, Alice will end up winning. So you can see this as the territories of the two players that are being controlled by their choices. Now the die will have a 1 over n chance of landing on any of the numbers. And if it lands outside your territory, you get $0. But if it lands in your territory, you get the corresponding z dollars. So this is why the expected earnings is basically related to the sum of the numbers in your territory. So Bob can do this and then evaluate whether to take the left side or the right side. But the question then is, okay, let's say Alice and Bob picks their numbers already. How do I assess whether Alice is in a better position or Bob is in a better position? Then this is where we look at the expected earnings. So Alice have a higher expected earning than Bob, if and only if basically the sum of the numbers in Alice's territory is more than 50% of the sum of all the numbers from 1 to n. So basically the potential value you can get is the sum from 1 to n, and then how much you control in your territory. If it's more than 50%, then that gives you a higher expected earning than the other player, right? So now if you go back to the question, before you even pick any number x or y, can Alice pick her number x to make Bob get less than 50%, no matter if Bob takes the left side or the right side? Because if that's the case, then Alice would be better, right? If Alice cannot guarantee this, like if Alice picks a number and Bob picks something that makes Bob get more than 50%, then it would have been bad to be Alice. But if Alice can guarantee that Bob will always get less than 50%, with her choice, then Alice will be the one who is more than 50%. Alice will be in a better position. So this reduces to this problem. Can Alice make Bob get less than 50% of the sum from 1 to n, no matter Bob takes the left side or the right? So let's think about this problem a bit more closely. So in the very extreme case where Alice picks all the way to the number 1, then the right option for Bob is obviously going to sum more than 50% of the available sum, right? So if you go all the way, as you move all the way, Alice picks n, then to the right of Alice, it will become 0% of the available sum. So because this decreases from more than 50% all the way to 0%, there must be some special value of k star where just before k star, to the right of Alice, the territory will still be more than 50%. But once you move to k star, then to the right of it, it is less than or equal to 50%. So this value of k star will be very important because it turns out that it will be good for Alice to choose this number. Why is that so? Well, already to the right of k star, Bob is limited to less than or equal to 50%. How about to the left of k star? Well, for this, let's look at the diagram over here. Because from k star to n by assumption, it covers more than 50%, this blue part here. So that means by taking the complement, 1 to k star minus 1 is less than 50%, right? Because over here is more than 50%, so the other side is less than 50%. Then noticing that this is basically the same k star here, so to the left of k star is 1 to k star minus 1. I just basically transferred this conclusion here down to conclude that even to the left of k star, it is strictly less than 50%. So actually, it is good for Alice to choose k star because, well, to the left is less than 50%, to the right is less than or equal to 50%. So if this inequality is strict, like if this k star is such that we don't actually get equality, we actually have strictly less than 50%, then k star is her best option and Alice is strictly better. Now, of course, you can check that this is actually her only option in this case because once you move one step up again to the left, it will now be Bob getting more than 50%. So I'll just leave this quick check to you. But in the case where this is strictly less than 50%, it's better to just be Alice and take k star. But if this equality turns out to be, if this inequality turns out to be equality, then actually both Alice and Bob are equally as good because for Alice, she can either pick k star and then Bob will pick this side and get 50%, Alice gets 50%, or actually Alice can pick k star plus 1 and Bob will pick to the left instead and get 50% and Alice will also get 50%. So there are two options for Alice in this case, and in both options, Alice will only guarantee herself exactly 50%. So to summarize this first part of the problem, well, no matter what, you will always want to be Alice because you'll either be better or you'll be at least no worse off than Bob. Now the question is, for which value of n then is this inequality actually an equality? So actually for this value of n, right, if you have used this value of n in the interview question, then you will be like potentially embarrassing yourself because someone might come up to you and say that actually it is equally good to be Alice or Bob. So you need to be careful and avoid these values of n. So let's take a look at this further. The question then is, for which value of n does there exist an integer k solution to this equation where the sum of the numbers from 1 to k is exactly 50% of the sum of the numbers from 1 to n. Okay, so let's take a look at this problem. And we have now transformed this into the part 2 of the video, which is not the Jane Street quant interview problem anymore, but a number theory problem. So for which integer n greater than or equal to 3 does there exist a positive integer k to the solution where this part is equals to this part? So if you'd like to take a look at this problem, you can feel free to pause the video and think about it yourself. But if you are just here to enjoy the solution, let's take a look at how you will solve this. So this is one of the common methods to solve a problem like this. When you want to find an integer solution, but you have a quadratic equation, then you just directly use the quadratic formula. So you write this as a quadratic equation and you can find, using the quadratic formula, what should the value of k be in order to be a solution. And then I just simplify this a little bit by cancelling out the common factor of 2. And then the thing is you want k to be an integer. So this square root is the part that imposes a condition on n. In order for k to be an integer, first and foremost, the square root part must be an integer. So before we go into that, let's also check the divide by 2 condition. So even if this is an integer, you might end up with a rational number, right? But because this is a odd number, if this is a perfect square and you take the square root, you'll get an odd number again. With the -1 here, you end up with an even number, which can then be divisible by 2 properly. So this means that the only necessary and sufficient condition is for this square root here to be an integer. And the nice thing is this term in the square root can be written as n squared plus n plus 1 squared. So this is a very nice form. So the question becomes finding all n greater than or equal to 3 such that n squared plus n plus 1 squared is also a perfect square. And this is now in the form of a Pythagorean triplet where the 2 numbers here in the leg are consecutive. So this is called the leg-leg twin Pythagorean triplet. And rather than going through solving for the equation to generate these triplets, I'll leave it as an exercise for you to look up on the various websites, which I'll post in the comment section below. And there's a very nice article that shows the different ways of generating the triplets. But in essence, the solutions for n then are 3, 20, 119, 169, and so on. And they actually obey a recurrence relation. So you can actually generate all the different n's that satisfy this problem. So for example, if n equals to 20, right, then actually k equals to 14 would be one of Alice's choice. The sum from 1 to 14 is exactly half of the sum from 1 to 20. Yeah, and by the way, 2023 is not on this list. The unique value k star that will let Alice be strictly better is 1431. So one of the viewers have correctly given this answer in the comment section of the quiz. So good job, and that is all for what we'll be covering in this video today. Hope you found the interview question interesting. And if you enjoy math videos like this, do subscribe to the channel. Stay tuned to the channel for more math videos, and see you soon.